For this example, I'd like to just do some computations with complex numbers, so numbers that have an imaginary part with them. So with example 1a, when we add complex numbers, you just add their like parts. So let's see, here we have 5 and negative 1 are the real parts, and then we have negative 2i and negative 6i are the imaginary parts. So I'm just going to group those together. That's 5, and we're adding negative 1 to it, so it's a subtracting 1. And then we have plus negative 2i minus 6i. So when we combine these like terms, we get 4, and then we have negative 8i, and that's it. So adding those two complex numbers together gives me 4 minus 8i. And with subtraction, it's an almost identical concept, except we're going to distribute this negative into the parentheses, and both those terms will switch signs. So here we have 30 plus 20i, but we're going to have plus 12 and minus 7i. So when we look at these two pieces together, I have a 30 and a positive 12, so that's going to give me 42. But then I have a positive 20 and a minus 7i, which is going to take me to a positive 13i. And that's simplified, and that's the final answer there. So adding and subtracting, not very difficult. And when we come down to C, where we are multiplying two complex numbers together, here you just FOIL it out. You just use the distributive property. So, 1 gets multiplied into the parentheses, and then I gets multiplied in as well. So what we have is, all right, we have 1 times negative 5, then we have 1 times negative I, so no problems there. Now, when we distribute the I, we get negative 5I, and then we get a negative I times I, which I'll write as I squared. So I multiplied these two things together. I have 4 terms. I just need to combine like terms now. So I have this negative 5. I have a minus I and a minus 5I, which is minus 6I. Then I have this minus I squared. And one thing to note is that I squared is the same thing as negative 1. So what I'm going to do is replace this with negative 1. There's an extra negative in front of it. So we get negative 5 minus 6i, but then we get plus 1, which when we add that at the front, we get negative 4 minus 6i, and that's the final answer. Now you can also, multiply something that only has one term, like in part D, into the parentheses. Works the same way. We have 4i times 8, that's 32i. And we have minus, and we have 4 times 9, which is 36. And again, we have this I times I, which is I squared. And just like in the previous part, we get 32i, but I squared is negative 1. So if we replace this with negative 1, we're going to get a positive 36. And you could leave your answer this way, but maybe I'll write it as 36 plus 32i. And again, just another multiplication on this very last part here. Let's see. This is kind of similar looking. Here we have an 11 plus 3i, and here we have an 11, but it's a minus 3i. This actually will cause something different to happen in this example. So, I'll start by distributing the 11, then the 3i, and see what we get. We have 11 times 11, 121. Then we have 11 times negative 3i, that's negative 33i. Okay. Well, now we get a positive 33i. And then for the last step, we get negative 9i squared. So what happens is the middle two terms I have are opposite in sign, so they just completely cancel. This portion here is just going to be 0. So we get 121, and we're going to get plus 9, which is 130. So anytime that you multiply a number like this, and then you just switch it to either positive or negative, just whatever it is opposite from here, you're always going to get that these middle two terms cancel, which is just going to leave us with a number that's real. It's not even complex. This piece here, this 11 minus 3i, is called the conjugate. It's where you take a complex number and you just switch it from positive to negative, and the product of these two things will always be a real number. To divide complex numbers, we got to be a little bit more careful here. We have to use kind of a trick to actually make this work out. We're going to use the conjugate that we used in the previous example. So let me show you what I mean. For this very first one, I'm going to write this as a fraction, 5 plus 2i, but that's divided by 4 plus 3i. What I'm going to do is I'm going to multiply this by the conjugate of the denominator, which is 4 minus 3i. But I don't want to change the value of the fraction, so I'm going to do the same thing to the top. I'm multiplying by 1, so it doesn't change the value of my fraction, but it will do something useful for us when we actually multiply these two things together. So we have to, I'll put some parentheses in here, but we're really distributing, right? We're using FOIL to multiply at the top and bottom. For the top, let's see, I get 20, and I get minus 15i. That came from distributing the 5. And then when I distribute the 2i, I get plus 8i, and then we get minus 6i squared. This I squared thing is going to show up a bunch. I just know it's going to become a negative 1, and it's going to make this last number positive 6. For the denominator, if I distribute the 4, I get 16 minus 12i. And now if I distribute the 3i, I get plus 12i. But now I get minus 9i squared. The nice thing that happens here is in the denominator, the imaginary part completely cancels. So let's kind of clean this up a little bit. Looking at several pieces, again, this is going to be a negative 1, which is going to make this a positive 6. When I combine that with the 20, I get 26. And then I have negative 15i plus 8i, which is a negative 7i. And in the denominator, all right, so again, these two pieces are 0. But here, again, I get this other negative 1, which changes it to a positive 9 at the end. And so we have 9 and we have 16, which gives me 25. And we're practically done at this point. You can break this up into two fractions, 26 over 25 minus 7 over 25i. And as strange as the answer looks, this is it. We wrote it as one complex number, 26 25ths minus 7 25ths I. So you can even do the same thing for this second part here, where we have 2i divided by 10 minus I. Same trick applies where you can multiply by the conjugate. So I'll go through this one a little bit more quickly, but we get 20i, then we get plus 2i squared divided by, I know the middle terms are going to cancel in the bottom, so we get 10 times 10, which is 100, and then we get minus I squared. All together, okay, let's see. In the numerator, we have I squared times 2 is negative 2 plus 20i. And in the denominator, we have 100. Well, that's going to be an I squared times negative 1, so that's 101. Again, kind of a messy answer, but here it is. Negative 2 over 101 plus 20 over 101i. And that's the final answer. For this last example, we're going to look at exponents, powers of I. And I've kind of listed them out where they increase. So we have like I squared, I cubed, I to the fourth, I to the fifth. And then I jump to this I to the 103rd power. The goal here is to look for a pattern between these. So let's start with I squared. I already know that that is negative 1. So if you want to know what I cubed is, well, you can just look at the previous step and you can just multiply by another I. So negative 1 times I would give negative I. And every time you want to move one step down, you can just multiply by I one more time. So if we're going from here to here, again, just multiply by I. We get negative I squared, but I squared is negative 1. Those two negatives cancel to give a positive 1. So if you look at what happened here, we have I squared is negative 1, then it goes to negative I, and then it goes to positive 1. Maybe to complete this pattern in here, we could even like go backwards. Like it might be helpful to write this in here as, well, I to the first, that's just I, and I to the 0 is going to be 1. And now our pattern emerges. We start at 1, and we go to I, then we have I, and we go to negative 1, then we go to negative I, and now we're back at 1 again. Like this pattern repeats. It's 1, it's I, negative 1, and negative I. That was for an exponent of 0, 1, 2, and 3. And what do you know? The exponent of 4 kind of loops right back here and gives us 1. So using that logic, I know I to the 5th should be I, but that makes sense. If 4 takes us back to 0, then 5 is going to match up with what we get at 1, and what do you know? That's equal to I. Now, if you want to know what I to the 103rd power is, a simple trick here is to divide 4 into 103. That's what this process is over here. It's telling you that, well, if the remainder is 0, your answer is 1. If the remainder is 1, your answer is I. If the remainder is 2, your answer is negative 1, and so on. So let's see, how many times does 4 go into 103? Well, let's see, it goes into 10 twice. Okay, now we get 5. And we have our remainder of 3. The answer here is going to turn out to be this, negative I. So 103 is the same thing as 4 times 25 plus 3. If I'm being very careful, I'll write this as, well, 103 is 4 times 25 plus 3. I can break this into I to the 4th to the 25th times I cubed. I know I to the 4th is 1. And I know I cubed is actually negative I. This all simplifies to negative I.